Hello, my name is Paolo Cipollini from the European Space Agency. I'm the mission scientist for Copernicus Sentinel-3 Next Generation Optical, and with my colleagues Craig Donlon, Stefan Dransfeld, Benjamin Koetz, I'm gonna show how this mission is going to provide enhanced continuity of the sea surface temperature measurements that are so crucial for GRIST. It's useful to collocate this mission within the wider Copernicus context to show you where it stands. You see, it's one of the next generation Sentinels. Is the evolution of Sentinel-3, which, however, is split into the topographical mission and the optical mission. So Sentinel-3 Next Generation Optical will provide the continuity for the visible observations that at the moment are made by OLCI on Sentinel-3, and for the visible and infrared observations that are provided at the moment by SLSTR. There are other two missions highlighted in this slide in the Copernicus expansion column, LSTM and SIMMER. Later I will highlight the synergies with those missions that also measure sea surface temperature. Sentinel-3 has got SLSTR, and it is a workhorse of operational oceanography. Sustained observation provided by SLSTR on Sentinel-3 and then indivisible by OLCI also on Sentinel-3 are one of the pillars of the Copernicus program, and they are very useful for a number of services like CMEMS and the land monitoring services. But for CMEMS, you have a quality of data like those that you see in this example of the coast of South Africa, where we see the Agulhas retroflexion, and these kind of data are absolutely crucial for the marine services of Copernicus. So it's important to ensure the continuity of the observations made by the current Sentinel-3 mission, but we want to go further. We want enhanced continuity. The primary objectives of Sentinel-3 Next Generation Optical, therefore, are just not only guarantee the continuity of the existing Copernicus Sentinel-3 OLCI and SLSTR, but also supporting the evolving user needs. And the users are asking for better temporal and spatial sampling, for better spectral sampling, and also for better performance across the board. And we need to make sure that we do at least as well as the best missions of the past. I'm saying this because for some aspects, for instance, AATSR was slightly better than SLSTR. And so in that case, we need to take the precursor as our goal, as our model, and try to achieve the performance of the precursor. I'm referring in particular to the stability of the radiometer. But having said that, SLSTR is very mature. It has evolved through the family of instruments from ATSR to AATSR to SLSTR. So we are not envisaging major changes in the design. ASLSTR will be similar, still with a dual view, which is absolutely crucial for the quality of the climate data records that have to be derived from these kind of measurements, but it will be enhanced. So the main enhancement is that we will have a 500-meter resolution for all channels. For SLSTR, it was only for the solar channels, whereas the thermal infrared was at 1 kilometer. For SLSTR, we're going to 500 meters. Then we are adding new channels, new solar channels at 440 nanometers, which is useful for aerosol optical depth. we will add a 1.24 micron channel, extremely useful for atmospheric correction, and then one to be chosen between 4.05 micron and 8.7 micron, most likely the second one, the 8.7 micron channel, because we have recently seen from science support studies that this addition improves the SST estimates further. We can get the already very good SST estimates from SLSTR even better with the addition of that channel and perfecting the algorithms. And then the oblique view, which at the moment for SLSTR is backwards, but it will be shifted to be forward as it was for AATSR, and this has been a request by the Mission Advisory Group, which is going to be confirmed by the Copernicus services at the moment, but I'm pretty sure that it will be confirmed, and it has a number of advantages. Certainly improves the quality of the aerosol in the northern hemisphere, which is a primary region of interest, of course, for the Copernicus mission. You see here a list of the proposed ASLSTR channels, and you notice highlighted in yellow the 4 that we are adding. At least 3 of those we will be able to add, maybe not 4. Like I said, we'll probably have to choose one between 4.05 and 8.7. And the performance values that you see in this table, of course, are provisional. They are being looked at by science support studies and subject to the reviews of the Mission Advisory Group. So those are TBC. In terms of the general design of the platform and the payload, the limits that we've got is to fit within a Vega launcher with an operational orbit around 800 kilometers asynchronous. There's about 290 kilograms available for AOLCI, 300 kilograms for ASLSTR. And you see some of the sketches of the concepts that have been proposed by the 2 consortia that have been looking at this in phase 0. Now we are in phase A of the mission development. I will quickly highlight the complementarities with LSTM and SIMR, 2 other missions that measure SST. LSTM is a mission with the objective to provide a high spatial temporal resolution thermal infrared observations of land and coastal regions, and the applications include the coastal zone management. So this will fill quite nicely the high resolution niche in the coast that SLSTR and ASLSTR will not get to. In fact, LSTM, as you see here in the key features, has got a 50 meters resolution, so it's a fairly high resolution with respect to ASLSTR, but with a longer revisit time, of course. So that's a clear complementarity here. And the SIMR, the Copernicus Imaging Microwave Radiometer, multi-channel radiometer with a big antenna that you can see in this artist view, has amongst its mission objective quite clearly stated to measure sea surface temperature with a total standard uncertainty of less than 0.3 Kelvin, with a sub-daily coverage of the polar regions. And in fact, there's additional objectives for the global ocean to measure SST, and then also to measure the sea ice surface temperature, which is also an important parameter. So my summary slide is that the evolution of Sentinel-3 SLSTR, which we've called ASLSTR, Advanced SLSTR, will bring the enhanced continuity and continue the climate quality SST data record, and of course continue to enable a lot of operational applications. In fact, possibly enable a few new ones. The main enhancement will be that the resolution goes to 500 meters for all channels, but there are new channels. The oblique view is brought back forward in the forward direction as it was for AATSR. And I should mention, we will create level 1C synergy products from AOLC and AES-LSTR combined in the same data file, co-register with well-quantified uncertainty, because we really want the synergy of the two instruments to be exploited at the very best. And the mission is highly complementary with the LSTM and CMON, as I've just shown to you. Thank you very much, and I'll leave you with a slide that has the mission advisory group for Sentinel-3 Next Generation Optical. These are the experts that are advising us and helping us to make the mission the best possible to continue the high quality SST measurements that are so crucial for GRIST. Thank you.